In this project, we were tasked with building a two-way laser communication circuit, and then be able to perform measurements and analysis. Each circuit has to take an input from an audio device, either a phone or a laptop, and a microphone, and transmit the signal using a laser pointer. Inputs have to be combined and transmitted as one signal. Inputs have to be independently adjustable from 0 to maximum. This signal must then be received using a photodiode, which is then amplified and played using a passive speaker, also with adjustable volume. The target has to be 50 feet away or farther, and the sound output has to be 70 decibels measured at 3 feet. First up was the transmitter circuit. For the music input, we use the music input as a simple voltage source, and then put it through an inverting op-amp setup with adjustable potentiometer so we can send the signal to 0. For the mic input, we use a simple series circuit with a 9-volt power supply and a series resistor to utilize the microphone. We then stole the signal from the positive node of the microphone and sent it through a high-pass filter. This filters out the DC offset that was created by the microphone. We then sent this signal through an inverting op-amp setup with a potentiometer to allow us to send the signal to 0. The two signals were then combined using a summing op-amp configuration. The series resistors for each signal were a potentiometer, which allowed us to independently adjust each signal and combine them proportionally. Then, using a bias T circuit component with a power supply, an inductor, and a resistor all in series with the signal, and a capacitor, we applied a DC offset to the signal, which allowed the laser to be consistently turned on and the signal to be sent through the laser. This is our final transmitter circuit configuration. You can see that the two inputs are independently amplified using inverting op-amp setups, and are then summed using a summing op-amp. A DC offset is then applied using a bias T, and then is sent through the laser. Next up was the receiving circuit. We receive the signal from the laser using a photodiode. This creates a linear voltage supply that is proportional to the signal that is sent to the photodiode. The signal from the photodiode is then sent through a high-pass filter. This removes the DC offset created by the photodiode. The signal is then sent through an inverting op-amp configuration with a potentiometer as the feedback resistor to amplify the signal and allow the signal to be sent to 0. This will be our volume control. The signal is then amplified again through an inverting op-amp setup to allow the signal to be amplified to a voltage that is usable in our circuit. The signal is then sent through a cascading op-amp configuration. It uses 4 identical op-amp setups with identical resistor values, which allows us to amplify the signal and multiply the current output of the op-amps by 4. This gives us enough current to power the speaker to allow us to reach our 70 decibel level measured at 3 feet. This is our final receiver circuit configuration. You can see that on the left, the photodiode is receiving the signal. It is then sent through a high-pass filter to remove the DC offset. It is amplified twice, back-to-back, one with a potentiometer as a feedback resistor to allow us to control the volume output. It is then sent through the cascading op-amp configuration to give us enough current output to power the speaker successfully. Using a simple 1 kHz sine wave function generator, we generated the signal that you see in this graph. This is the input from the audio signal. The second graph you see is the measurement taken at the photodiode. This is the signal that is transmitted and received once the DC offset has been removed. This third signal is the signal that you see that is sent through the speaker. These 3 signals are how the signal is changed and adapt as it passes through our circuit. This is a graph of the frequency response of our circuit. It is the output voltage across the speaker versus the frequency of the signal that is transmitted by our circuit system. As you can see in the graph, our circuit functions most effectively between 70 Hz and 30,000 Hz.